All right, everybody, let's get started talking about mathematics of finance. So it's time for me to say something that, there's no gentle way to break it to you. There's a lot of algebra in this course. So if that just made the hairs on the back of your neck stand up or, anything, I apologize. It's kind of the nature of the beast. Maybe you have a strong algebra background, maybe not so much. One way or another, we're going to spend this first chapter kind of kicking the rust off the bike chain, because even if you were good at algebra, it may have been a while since you've had to do it. So that's where we're going to be kicking things off in this first chapter, playing around with kind of the, I don't like to say basics, but yeah, the basics of algebra in some sense. So the first section we're going to be dealing with, I'm working off the guided notes file that's posted in Moodle, so yeah, I take for granted you've got that thing handy with you while you look at this. It talks about algebraic equations. The key thing to remember about an equation is that it says two things are equal. So we need an equal sign, like just, something by itself without an equals, that's what we normally call an expression. It's a fine point, but it's one that I kind of end up, thinking about a lot. So as an example of an algebraic equation, I'm going to write this guy right here. So 2x plus 3 equals 7. You've probably seen something like this in an algebra course at some point in your mathematical history. So just getting down some of the lingo, this x here, that's what we would generally refer to as the variable in our equation. You may also hear me call it an unknown, just to keep that in the back of your mind if it comes up. So it's kind of a placeholder. It covers potentially any one of a range of possible x values we could try to plug into this equation, so to speak. This number 2 in front of it, that's something that we generally refer to as a coefficient in our equation. So there's just like an implied multiplication going on right here. So that's sort of the thing that we're dealing with. Now, in terms of just talking about equations, just having the thing is nice, but generally speaking, you probably remember having to solve these things. You've most likely seen solve for x in front of a block of homework exercises. Again, sorry if that brings up painful memories, but it's where I gotta go, right? So you may, we'll talk about how you'd actually go about solving something like this momentarily, but you could just sort of do like what you might call the guess and check approach, like find what's a number that when you double it and add 3, we get 7. That would correspond to x equals 2, and that's the solution to this particular algebraic equation. We'll periodically want to talk about the solution set to an equation. So if something like that comes up, the solution set, we're sort of going back into like your finite mathematics history, if you think about that. So we would write it in that case with like the curly braces to denote a set. So we would have the set containing 2 as the solution set for this particular algebraic equation. So far we've hit some of the lingo, got a little bit more to go here. It talks about equations that are true no matter what the value for x is. That's something that we refer to as an algebraic identity. We don't really need too many of these over the course of Math 210, but it does come up, and I actually worked for a bit to come up with something that really worked as an identity. And it's not, it's not terribly original. It's basically just like kind of canceling common terms from a fraction. So 3x over 6, x over 2, again, if you cancel away to 3, you see how that works. No matter what value I tried to feed in for x, this is always going to be true. So that's an example of an algebraic identity in action. Okay, so the last thing I wanted to mention lingo-wise is it talks about equations being equivalent to each other, and that's going to be important when it comes to solving these things. But the idea is two equations are equivalent if they have the exact same solution set. So as it turns out, these two guys right here, 2x plus 3 equals 7 and x equals 2, they are in fact equivalent in an algebra sense, because the only value of x that makes this work is x equals 2, and then, yeah, the same thing happens here. You plug 2 in here, you get 7 equals 7. If you plug 2 in here, you just get 2 equals 2. So both equations check off, and no other x value will work. So no x value satisfies the equation, if you will. So those two equations are equivalent. You could get a little more technical with it, but you don't necessarily have to. All right, so now, in terms of how we go about actually solving this equation, you may recall having talked about inverse operations at some point in the past and sort of, working to isolate a variable. At the bottom of this first page of notes, it lays out sort of how you can solve what we call a linear algebraic equation. to get, sort of to get the x variable by itself. The idea is that you sort of walk through these steps, and each step of the way, as you're making adjustments, all of the equations are in fact equivalent to each other. That's what these inverse operation principles end up doing for us. So I'm not going to take video time reading what's on the PDF. You've got that. Let's see how the method works in the context of some more examples. All right, so get that guy cleared off here. All right, example number 1. We have 3x over 5 equals -6. All right, so now we want to get the variable x by itself. That's the idea of solving for x in this instance, right? So following through our procedure, it mentions getting rid of denominators. If you have a fraction, that's a common thing. Technically, you could try to work with fractions in some cases, but for a lot of people, fractions are scary, so let's get rid of them. So the idea here is let's come up with some way to get rid of this division by 5. This is where the inverse operation thing comes in. And so to get rid of the division, we can multiply. So I'm going to multiply both sides of my equation by 5. All right, so that's not the clearest 5 I could have written right there, but hopefully you can make it out. So that's what we're dealing with so far, and those two guys knock each other out of the equation, so now we no longer have a fraction. That may make you feel a little bit better about this. Always remember, whatever you do to one side of an equation in something like this, you got to do it to both sides. So all we've got left on the left-hand side of this equation is 3x. -6 times 5, you can work that out, calculator, by hand, whatever. So we have 3x equals -30. All right, well, is x by itself yet? No, it's still got this coefficient of 3 here. What can we do to get rid of that? Well, we said earlier there's an implied multiplication. To undo a multiplication, we can divide. So divide by 3 on both sides, and whoops. Don't call that equals. Don't do that. All right. So those guys go away, and now all that we have left on the left-hand side is just the variable x. And so -30 divided by 3 gives us -10. I like to put a little box around my solution so that I know we've got our answer here, and that kind of sets things up for us. It has just dawned on me, I've got some technical difficulties. Bear with me for just a moment. All right, I took that moment with the technical difficulties to go ahead and write up the next equation that I want to take a look at. So this is the next example rolling along through here. 4x minus 2 divided by 3 on the left. On the right-hand side of our equal sign, x over 2 minus 4. So now in this instance, we want to get rid of our denominators. We could technically do this in 2 stages, multiply both sides by 3 to get rid of this 3, multiply both sides by 2 to get rid of the 2, but that's where the directions suggest finding a common denominator. So instead, let's multiply both sides by 2 times 3, or 6. Okay, so over here, that 3 is going to go poof. That 6 cancels down to where all we have left is a 2. Over here, we need to be a little more careful because we actually have this subtraction here. We need to use what we call the distributive property in order to maneuver what's going on here. So both of these guys need to get multiplied by 6. Make sure to remember that. Failing to distribute is a common mistake I end up seeing here. So now on this side, we have 2 times 4x minus 2 again. I'm going to go ahead and distribute that 2. So I'll have 8x minus 4 over there. Over here, I distribute the 6 onto each of these guys. 6x over 2 is going to be 3x. I canceled the 2. Minus 4 times 6 gives me minus 24. All right. Now, this time around, it's a little more complicated than what we saw in that previous example, right? We've got x's on both sides. We've got constants, or numbers, on both sides. So what we're going to do is move all of our x terms onto one side, again, using these inverse operations, move all of our numerical terms that don't have an x over to the other side. So what do I need to do here? Well, I've got to subtract a 3x, so I get all of my x terms on the left. You could do it the other way, but all right. So I don't necessarily recommend that you do all this like lining stuff up, but it works out okay. So that would take care of those two guys. Awesome. We've got a minus 4 over here. Well, let's add 4 to both sides. Poosh, poosh. Again, whatever we do to one side, we got to do to the other. Like I said, I don't really like the vertical lining up. So negative 24 plus 4. Okay. So now we can kind of collect our remaining terms because now all our x's are on the left, all of our numbers are on the right. So 8x minus 3x, so we have 5x is all that's going to be left over there. Negative 24 is 4 is going to give me a negative 20. Now we're basically back in the situation like we had before. So divide both sides of my equation by 5. The 5 next to the x cancels out, and we'd have negative 20 divided by 5 on the right. So my solution in this case would be x equals negative 4, or as a solution set, if you wanted to write it in the set notation, you could do the curly braces with negative 4. All right, so that's a couple of examples of this algebraic process in action. We're going to take a look at some more examples of this in our next video, and then sort of transition into seeing some additional ways you could try doing some algebraic manipulation. So stay tuned.